Yes, welcome everyone. Today we are looking at quantum physics. I have the following questions. The first question we are going to address is from Cambridge, October-November 2023 paper. It was question 8A, just the first part. It is paper 4, the structured questions, paper 4, variant 1. It's from there, just the first part. The question says, show that the momentum P of a photon of electromagnetic waves is given by P is equal to lambda over A over wavelength. Planck's constant divided by the wavelength. Okay, let's go straight into that, then I'll read the rest of the questions later. Okay, right. To show that the momentum of a particle is moving in space, a particle moving in space like a photon moving in space is momentum. We have to use the equation which is E, the energy is equal to P, I remember it more as PC, right? Or you might remember it as P is equal to E over C, right? This equation stems from but I'm not sure, I don't think you'll be required to know that where it comes from. It comes from the equation E squared is equals to M squared C squared plus where we assume that the photon does not have a rest mass, so this M will be 0, so this whole thing will be 0 plus the P squared C squared. This P being the momentum of the photon and C the speed of light or the speed of electromagnetic waves, right? So this is 0, this gives you this. But for A level, just start from here. The momentum is equal to E over C. So we need to prove that we can rewrite this as this. So your E is the energy of the photon, which is given by HF. So you can rewrite this as P, right, equals HF over C, right? But F from the equation C is equal to F lambda, right? Your F is C over lambda. So if you replace F there with C over lambda, can I write it? You will see that your momentum of a photon is given by H over C times F, which is C over lambda from there. Right. So the C is cancelled, which now, so all you are required to do is to say the momentum of your photon equals the Planck's constant H divided by lambda. Proved. I think this was 2 marks. You say proved. Okay. That's all you're required to do. This equation is very useful. We normally write it as lambda like this. The wavelength is equals to H Planck's constant divided by the momentum. And remember, you can always replace this momentum with the mass times velocity if you are given the mass of the particle, like mass of an electron, mass of a proton, those kind of particles. Those are the particles, small, according to de Broglie. This is called the de Broglie's equation. The small particles when they are in motion, they have wavelength. This is the de Broglie's equation, right? Right. There's a follow-up questions there about the beams of light or of electromagnetic waves hitting a surface, and you have to calculate the power. Remember, power is intensity times area, right? And if you want the number of photons or the number of particles hitting a surface, you know that you have to divide your power by the you divide power by the energy. Power is joules per second divided by joules, so that you get the per second, the number of heating per second. And also you have to calculate the force and the pressure. And remember that the force will be equal to the change in momentum, right? And the pressure will be the force per unit area. So all that, I'm going to look at that in a separate video. So I'll follow up that question with that. But for now, I just want to tackle these questions quite quickly. If we still have time, let me see if we can quickly do those questions. So, right, this is powerful question, H over. The first question there, I think, is the relationship between lambda and EK. Yes, that's a good one. You see, the wavelength there is h over momentum. Right. Now, how can we relate this momentum to half mv squared? You know that our kinetic energy is equals to half mv squared. But we want to write it in this form. So if we multiply this side by m, so if we say AK times m will be equal to half m squared. Whatever you do on the left hand side, do the same thing on the right hand side. Right? You see this equation? This is equals to that. Good. Then it means your m squared, v squared, is equals to 2 times kinetic energy times the mass. So if you square root both sides, here you get p, here you get the square root of 2ekm. Right. Which means you can rewrite this equation as, can I write here? Here, as lambda wavelength is equals to h over square root of 2 times the kinetic energy times the m. Now you notice that the Planck's constant there is a constant, the mass is a constant, the 2 is a constant. So therefore there is a relationship between the wavelength and the kinetic of the energy of the. Obviously, the higher the kinetic energy, the lower the wavelength. The wavelength, the relationship is such that it is directly proportional to, inversely proportional to the square root of the kinetic energy. Okay, so which means you can have this relationship. I think I promised you calculation similar to this. Can I remove this? I think I've got this one right. If we now say the EK, we now say lambda. If you look at that question, what is the impact on lambda if the kinetic energy of the particle it decreases by a factor of 3? So it will be lambda is, we say that lambda is equals to the square root. We said lambda equals h over the square root of ek, not equals, is proportional. We said we just not to put too many things, like I promised last time. Lambda is directly proportional to the inverse of the square root of the kinetic energy. Just use direct proportionality without an equal sign. So what happens now if you decrease? Yes, good question. Decrease by a factor of 2. So your lambda u, I like to use nu, will be directly proportional to, you've decreased it by a factor. So your EK is decreased by a factor of 3. So you are decreasing it by 1/3. Yes, by 1/3. That's what it means, decreasing by a factor of 3. Right? So what then happens if you compare this and that? Let me rewrite your lambda nu as lambda nu, so that it looks similar to this, will be directly proportional to 1 over 1 over root of 3, because the square root of 1 is 1, times the square root of ek over 1, which is just square root of ek, which is similar to this. This whole thing is 1 over this now goes to the top. So if you do your lambda nu divided by lambda, you will see that mathematically that it will be, just for the sake of time, it will be square root of 3. So you increase your, when you decrease the momentum, decrease the speed of the accelerating particles, you increase your wavelength by a factor of square root of 3. Well, this will cancel. Okay, good. Then if last bit says calculate lambda of an electron that is accelerated through a potential difference of 100 volts. So what we are going to do there is we have to calculate the electron volts. So your electron volts will be, the voltage is that an electron, the charge on an electron is E times the voltage. So it gives you the electron volts. So let's just call the charge on an electron E times 100. Okay, so that will be 100 electron volts is the kinetic energy of the electron, right? So your kinetic energy will give you, let's convert that to joules. You have to convert the kinetic energy to joules. So that you multiply that by 1.6 times 10 to the power negative 19, which is to change to joules first. Then we have we want the wavelength is equal to 1 over, this is the kinetic energy, so this is Ek. So it's 1 over, we said, it's h Planck's constant over the square root of 2 times the kinetic energy, which is this one, right? You put all of this there, right? All of this is just to be joules. Then the times m, the mass of an electron, 9.31 times 10 to the power 31. For the sake of time, I don't need to do the calculation. So I hope you follow this. This is especially for the Cambridge A-level students. Thank you. Thank you.